Wigderson clearly needs no introduction because everybody showed up to see him. Our wise man in town at the IAS for many years, leader of the field. So, without further ado.
Thank you. So I don't know, I asked Sanjeev, the question I ask every time I come to this room, why don't you use the auditorium downstairs? You have a beautiful auditorium which everybody can see the slides, and well, maybe if you rebel, you students, if you, those in the back who want to see and here you can ask for this theory seminar to move downstairs to the small auditorium. Okay, so this is my, my rebel part. I want to tell you today about operator scaling. So it's work that started here with two graduate students up to last year, Ankit Garg and Rafael Oliveira, and with Leonid Gurwitz, and then there are lots more work and that followed up. I'll tell you what I like about this. So it's a long story, but it's a long story. I put my new book commercial here because the title is Math and Computation, and I think that this particular work, which starts in complexity theory, connects with lots of areas of math, as you'll see. So the focus will be just one computational problem and one algorithm. The computational problem is what we call PIT, Polynomial Identity Testing, which I'll call today singularity or symbolic matrices. I'll define it. The one algorithm I want to talk about is alternate minimization. It's a well-known heuristic in optimization, machine learning, and so on. We'll try to apply it to this problem and analyze it. And from this study, and suddenly without any intentions, it turned out to be connected to lots of areas of math and physics. In fact, here is a list, and this list is partial. We'll see most of them. We'll see non-commutative algebra, we'll see invariant theory. You don't have to read the black parts. We'll see quantum information theory, and I'll at least mention the connection to analysis. As I said, the problems we set out to solve are in computational complexity, having to do with algebraic identities, polynomial identities, and also connected to lower bounds and de-randomization. And the one really interesting thing is that this problem, the one problem we are studying is an algebraic problem, but despite it, the tools we'll use is, our tools from optimization, from continuous optimization. And as it happens, these algorithms that we'll use to solve this problem turn out to optimize over non-convex non-convex objective functions, and this is interesting in itself, and I probably will not have much time to talk about it unless you ask, but it leads to solutions of problems that along with the rigorous analysis of things that we don't normally are able to do. So it's a new hammer that hopefully will be used for some new nails. Okay, so let me tell you about the problems and the algorithm, and then we'll start the analysis. The problem, actually there will be a couple of problems. This is like a baby problem of the problem we want to solve. It's not obvious that it's a baby problem, and I'll explain why it is. So this is bipartite matching, the one you know and love. Have two sets and the graph between them, and we want to know whether you can match up the left vertices to the right vertices perfectly. In this graph you can do it. Right? And in this graph, you cannot do it. In this graph, there's a, these two vertices are not connected to, are connected only to this vertex. So there's what's called a hole blocker. A Hall theorem tells us that there is no perfect matching in this graph. So these are not yet algebraic problems. That's combinatorial problem, we would like to make it algebraic, and we'll do it in 2 steps. One step already makes it algebraic. You look at the adjacency matrix, and what is the matching here? So this is the adjacency matrix of this graph, right? So the left vertices on the row, the right vertices on the column. We write a 1 if there's an edge. And matching is a diagonal full of 1s in this matrix. And that's what we are looking for. So the question turns out to be to compute, this graph as a perfect matching if and only if the permanent of this matrix is positive. What's the permanent? Maybe this door is blocking someone. Oh. What is the permanent? The permanent is just like the determinant, but without the sign. So you just count, you go over all possible diagonals and you add them up without signs. So it's very easy to see that there is a perfect matching here if the permanent is positive. And okay, that's a problem. What's the best algorithm? What's the complexity of this problem? It's in polynomial time. Who knows the origin of this polynomial time algorithm for matching? This is actually 1890. Jacobi, one of the Jacobis, I'm not sure who. I mean, I knew, but I forgot. Needed to solve a system of ordinary differential equations, and he wanted the most efficient way to go about eliminating variables, and this was the way to do it. So, yeah, it was known for a long time. So we have a polynomial time algorithm for this, and therefore for this algebraic problem, but the permanent, as many of you know, I'm not going to talk about it much here, is a complicated function, so we can test whether it's positive, but we cannot compute it, for example, as far as we know. So Edmonds, now we get to Edmonds, had another idea. He found another way to algebraize this problem, and one way to a related matrix to consider to the adjacency matrix is a matrix of variables. He said, let's put, instead of 1s, let's put for every edge that appears, we'll put a distinct variable. Okay? So there's an edge from 3 to 1. We put x3, 1, so we put distinct variables where there are edges, zeros where there are no edges. Okay? And he observed, so this matrix, this symbolic matrix, he observed that now we can test the perfect matching in this graph by evaluating the determinant of this. The determinant of this matrix is a polynomial, right? And it's identically 0 exactly if there is no perfect matching. Why? Because if there was a perfect matching, this monomial that you'll get cannot be cancelled with anything else because all the variables are distinct. So I'm going slow, but please ask me questions if anything is unclear. Okay, so we can test this for this type of matrices. We know it's a problem is polynomial time, but then Edmonds had a brilliant idea, is to generalize this problem. And said, well, this is a case where we have single variables and they are all distinct in the matrix, but suppose we just look at the matrix of linear forms in general over some number of variables. So here is the problem. These are what we call symbolic matrices in general. We have a bunch of them over some field. The questions will be interesting over every field, but we'll mainly work with the rationals today. And every entry is occupied by some linear form on these variables. Okay? And you can ask the same question. So this is L of x. You can ask the same question, which is, we call the polynomial identity testing problem, which is I would call it singularity. Is the determinant of this matrix identically 0? Okay, so the input are these linear forms, and the question is whether this is...
so number of variables is...
some at most n squared. So without loss of generality.
It's n squared.
Yeah. So that's a problem we want to solve. That's a big problem, and we'll see why in a second, and we will not be able to solve it. So that's where I ask for your help after the lecture. So that's what Edmond asked. Is the polynomial time algorithm for this problem? Now, I'm sure many of you know that there's a very simple probabilistic polynomial time algorithm. And even if you don't know, you would find it. What's the randomized algorithm, you just pick random values for the variables. Small integers will do, and evaluate it. Of course, if the determinant is identically 0, doesn't matter what you plug in, you'll get zeros. But if the polynomial is not identically 0, then with high probability you can prove that you get a non-zero, so it's a very good probabilistic algorithm.
So finite fields, right?
You can do it over any large enough field. If you have more than n elements, more than the degree elements in your field, this works.
So for reals, we can just evaluate
them. Small integers, yeah, and integers 1 through 2n. Okay. Yeah. Okay. So the problem is just a problem of de-randomization, right? Just simply eliminate the randomness from this algorithm, which we can do sometimes. So at this point, it looks like, okay, that's a problem, but we have many problems. Everybody here has their own problem. This is a somewhat more important problem than most problems. And let me tell you why. A lot hangs on it. One is that Valiant discovered, Valiant's completeness theorem is that this problem, just testing singularity of symbolic matrices, is really, it really captures proving all algebraic identities. Any algebraic identity faced in math can be represented this way. So as mathematicians are really keen about proving algebraic identities, they would have loved to have an algorithm for this.
Wait, what? Say that again?
So every algebraic identity that you find in any mathematical text can be converted, as you should know, to a matrix of linear form. Then it's an identity if and only if the determinant vanishes identically. Okay, that's Valiant's completeness of the determinant.
Is this even for like not?
I see. You're saying just a circuit.
Yeah. Sorry. Yes.
Does it have to be polynomial identity, or is it any?
Yeah, polynomial identity. Yeah. If you have signs, it's a different thing. Yes, that's what I meant by algebraic.
But the randomized algorithm is good enough for this, right?
The randomized algorithm is good enough for this. Yeah. So let's see another reason why it's important. So why do we care about the deterministic algorithm? Everybody is happy to toss coins.
So by the way, algebraic identity is like a formula. Is it right? Or?
It's a formula.
I see.
Yeah, that's what mathematicians normally use. So here's another reason, which is was sort of shocking when it was discovered, 2001, is that if there is a deterministic, now deterministic is really important, that is deterministic polynomial time for this problem, then something like P is different than NP. I'm not going to explain this. This is the algebraic version of P and NP. This is a different talk. But now you see, in fact, one should stare at this for a minute and appreciate this result. An algorithm for one problem implies that another problem is difficult. In fact, this would prove that the permanent is hard, exponentially hard. If you find the polynomial time deterministic algorithm for testing symbolic identities, you have proved a separation like P different than NP. So now it's, we have better reasons to look at this.
I mean, it's not quite. But
not quite, but as some of you know, I like to cheat in talks, but it's in the state of our knowledge. It's not a big cheat in that in the state of our knowledge of complexity theory, unable to prove any lower bounds, this will be major and will prove something like it, and hopefully will.
Sorry to press.
Yeah.
What's the fine print on this statement?
So this is almost VP different than VNP.
No, wait. There's also the next minority.
Yeah.
Okay.
Yeah. So that depends. It's actually it depends on how you prove this. There is you can prove it in two different ways. One way will give you VP different than VNP. Another will give it either this or another Boolean lower bound. But yeah, I don't want to go to the fine print. I just want to tell you this is an important problem, and we don't know how to solve it. Okay, there are many reasons that mathematicians have to looking at singularity. It turns out to capture the maximum rank in a space of linear space of matrices. It appears as a modular isomorphism problem, as a graph structural rigidity problem, and others. In other words, it's a really interesting problem. And I told you already, we are not going to solve it. So what are we going to solve? So here's the problem again. We are given a matrix of linear forms. Let me suggest the following representation for it. How do you represent a matrix of linear forms? You know, you can take the matrix which is the coefficient of the first variable, as A1, the matrix which is the coefficient of in other words, you get this linear combination, and these matrices are matrices over the field. So the input to that problem is a tuple of matrices, and we ask whether this linear combination is singular. So we asked really whether the determinant was identically 0, and this is the same as this matrix being singular. Singular where, in the case that we are looking at, in the case that the variables are commuting, this is they are singular over the field of rational functions over these variables. And as we said, we don't know if it's in P. Now, what we are going to do, as you can guess from this, is change the problem and look for a problem we can solve. This is a problem where exactly the same problem, ask whether a matrix is singular when the variables do not commute. Now this is a very bizarre, you know, where should it not, where are you trying to invert this matrix? Where is it singular? Well, it turns out that there is a field, which we'll see later in the talk, capturing the same thing that this field is doing. It's just completing the polynomial ring into a field. But it's a very bizarre object. And it turns out that this problem is actually interesting in its own right and appears in various places, and we'll see that too. And it's not even, unlike this one, which is clearly decidable in exponential time, this problem, it took time to even prove that it's decidable. And then Kohn and Rethenauer proved an exponential time upper bound. And that's where it stood, randomness or no randomness. And the algorithm I want to tell you about is one that puts it in P for the rationals. And following it came another algorithm of Ivanios, Chiar, and Subramanian that does it, in fact, for every field. So this is a paper I mentioned that started this chain with Gar, Gurwitz, and Oliveira. And I'll talk about this one. Okay, I want to explain this algorithm. So this is the result. I didn't really tell you what problem we are solving because I didn't explain this, but we'll see more elementary descriptions of this problem of singularity in the non-commutative case that will not require understanding this. Okay, so that's a problem.
So
Question?
not commuting means not addition and multiplication?
No. The multiplication does not commute.
Addition still?
Yeah, addition commutes. Addition is sort of over the field. It's just when you so if you think about just polynomials, forget division. I mean, the whole problem is division. We are trying to invert. But polynomials, the xy is different than yx. That's what.
Matrices, right? So
What?
they're essentially matrices.
It's not essentially. There is. We'll see later. But yeah, you can think of matrices. These are formal variables at this point. Yeah.
Is there any intuition why non-commutative case is easier?
So Nadav, I don't know if you heard. Ask if there's any intuition why the non-commutative case is easier. So first of all, we don't know that it's easier. First of all, it used to. Well, I say it, but if we talked 3 years ago, it looked harder.
That's what I was.
So it doesn't. It's not clear whether it's harder or easier. Our state of knowledge currently makes it easier than this. It used to be harder than this, and maybe tomorrow you will make it even easier. So I don't know. There is intuition, yes. The intuition is complicated to explain, but the fact that you don't have the non-commutativity adds structure, and maybe you'll see some of this.
So what about a trivial randomized algorithm for the problem?
No, there is no, there is none. I mean, if there was an algorithm, any algorithm, not necessarily trivial, you will have an exponential algorithm in that, right, triangle, right, so there was none, yeah.
So it will imply decidability in
Yeah, in particular, yeah. There was nothing trivial.
If you substitute random matrices for the axis,
What size?
big enough and squared.
We'll see at the end of the talk. Yeah, that's a very good. This is a very good. Yeah, I tried it, but it turns out that, and in some sense, this turns out at the end we'll see that such an algorithm would work, but it requires a lot of developments in non-commutative algebra and in invariant theory. And I want to explain this connection.
So just counting doesn't cut it?
No,
You can-
no, definitely not. It's not clear that there is any bound on these matrices, at least if you're sitting at Hilbert's time. It's not clear it's finite even. Without Hilbert, you don't even know that there are finite matrices. So we'll get to this, hopefully. I don't know how. Where we'll get to.
It's easier because there are just fewer identities. Like, it's hard to have a non-commutative identity.
It's harder to have a non-commutative identity, although this in itself doesn't say why it should be easier to test. It's a different problem. It's a different problem. There is more rigidity in the problem, if I can, it's very hard to give intuition at this point. But yeah, there are reasons with lots of hindsight why it's, also there's a lot of theory that works there and doesn't work in the commutative case. Okay, let me go to the algorithm. Okay. So I want to talk about one more problem. And as you'll see, it's not a different problem. It's the same problem. So here's the problem. Matrix scaling. Some of you may have seen it. The input is a single non-negative matrix. So let's say real matrix, like the adjacency matrix. And we want to scale it. So first, let me define a doubly stochastic matrix. Matrix is doubly stochastic if the sum of rows, sum of columns is 1, okay? We want to make a matrix doubly stochastic using scaling. So what are we allowed to do to make it? We are allowed to multiply rows by constant and multiply columns by constant. In other words, multiply from the left and from the right by diagonal matrices. So what you want to do is do this and make it doubly stochastic. Again, well, maybe we'll ask why in a second, but sort of from a very questions, I hear whispers, but from a sort of high-level mathematical point of view, you say, well, that maybe it's possible, maybe it's not. The problem is fair. There are 2n degrees of freedom and 2n constraints. Yeah? Only you are multiplying and you want sums, and it's not clear. Okay. So doubly stochastic scaling is the question. I give you a matrix. Do there exist scaling factors that will make it doubly stochastic? And I want to stress that I'm happy if you can just make the row and column sums arbitrarily close to 1. They don't have to be 1. This turns out to be the right problem to look at. There is another problem. You want to make it equal to 1, but that's a problem we are asking. And why are we asking this? Because this problem turns out to be exactly, let me say it here. Because this problem is exactly the problem of testing whether the permanent of this matrix is positive. It's not difficult, it's a nice exercise, I leave it to you. Okay? So it's a problem we wanted to solve, the first problem I talked about. You can ask why people looked at this, and actually there are great reasons. It started with Singhorn, and maybe even earlier from numerical analysis. It appears in signal processing. We used it in our paper. I'll talk about a little more soon on approximating the permanent, and it is equivalent to perfect matching. And there are many algorithms for this. It's an important problem in itself. Yes?
So, what level of approximation do you need for it to be equivalent to permanent of A testing non-negativity?
Yeah, we'll see in a second, yeah. But at this point, the definition is you are asking whether for every epsilon you give, there are scaling factors that will make it within 1 plus epsilon, plus minus epsilon. Yeah. Okay, so that's a problem. And I want to describe the algorithm for this, because the algorithm for this is like a perfect matching was a toy problem for the singularity problem. And an algorithm for it will be a toy algorithm for the algorithm for operator scaling, as we'll see. I didn't define operator scaling. Okay, so I want to tell you what the scaling algorithm, or what the alternate minimization algorithm that we'll keep using looks like in this case. So again, we have a non-negative matrix. We want to know whether we can scale it or not. And remember what we need to do. We are asking whether we can multiply the rows and columns by constants so that the row sums are 1 and column sums are 1. And there is one observation here. It may be difficult. It's not clear how to coordinate this. But at least half the problem you can solve. You can easily make the row sums 1, right? Everybody agree? Yeah. So this is a key to alternate minimization algorithms. It's, you know, you are really, and maybe we'll see at the end some more, you are given a problem with several parameters, and optimizing it or solving it is difficult. But if you fix all but one of the parameters, it becomes easy. So here you have rows and columns. You want to just make it row stochastic, it's easy. So let's do it. And then you do the other one. So let's do it. So scale rows, so here is how you make all the rows are, sum 1, but that the columns are not. So let's make the columns 1. Okay. And now the rows are not. And let's make the rows 1. But now the columns are not. But this seems to be going somewhere. Well, maybe not. It's actually not going very well, because that's where it's going. But actually, it's not bad that that's where it's going, because, you know, there's no convergence here, but this graph didn't have a perfect matching, so maybe something good is happening. So we'll soon do another example. I just want to, you know, just formally write down the algorithm. It's an extremely simple algorithm, just you see. I mean, in general, the alternate minimization algorithms are simple. So just for notation, we have some, you know, either the sums of the rows inverse, that's what we multiply on the left, or some of the columns inverse multiply on the right. We know that these guys are not 0, because if there were 0, there was no scaling. I mean, if some row is all 0, you cannot scale. Anyway, and this is the algorithm. You just iterate. You multiply on the left, multiply on the right, multiply on the left. That's what we are going to do. We'll do it again. That's, as I said, is the alternate minimization heuristic. Let's do it on this other graph that we saw in the beginning. Here, of course, there is a perfect matching. This other graph. And let's try to do it in this case. Okay? So here we scale the rows, scale the columns, scale the rows, scale the columns. And, well, you may have seen that, you know, these entries are shrinking while these are growing, and that's the limit, turns out. Which is good, because, as we said, this graph has a perfect match. And this is a general phenomena, so here's the algorithm. In general, what you do is you run it. Turns out that n cubed steps is enough. What you test, to your question, how well you should try to approximate it, up to 1 over n. And, you know, either, so you are generating a sequence of matrices up to the last one. You just look at the last one. Let's say the rows are completely, you know, stochastic, and the rows, you know, you check if any one deviates. You say no perfect matching. If the no deviation, you say there is a perfect matching, and that's it. That's the algorithm. So now I want clear what the algorithm is. It looks totally naive and maybe stupid, but it works. So, and not only does it work, I want to tell you that the analysis is extremely simple. Now, there are several analyses in the literature. I'd like to give the one from this paper with Lina Samornitsky, the one that talks about approximating the permanent. And it's the following. You need, what do you need when you analyze an algorithm, a dynamical system of this thing you want to show convergence? You need some good progress measure. And for this progress measure, you need 3 properties always, you know, that it starts somewhere, that it improves, and it cannot go too far. So the permanent of this sequence of matrices will be our progress measure. Simply this function. Even though we cannot compute it, we can define it. And it's very easy to prove these 3 properties here. One is that there is an upper bound on all the values. It's never more than 1. The permanent is never more than, let's say, the product of all row sums, and these are all 1, or the column sum. So this is easy.
So we are assuming that each entry of the matrix is between 0 and 1?
No, after one step of scaling, yeah, just start from the, yeah. The second thing is the growth, that every step you grow. And, you know, so when I put this little star here, I mean, you grow if there's room to grow, if you are already close to if you are close to 1. then you don't. But if there is room to grow, you grow by 1 plus 1, 1 over n. So that's a lot of growth per step. And this is also easy, just arithmetic geometric mean inequality. It's really easy. And the third step is that when you start, you don't start too low. Turns out you start in the first matrix after the first normalization, exponentially in n. I guess I'm doing this just for, let's say, 0, 1 matrices. If you do it for arbitrary matrices, n will be replaced by the bit length of the entries or something. So anyway, from these three properties, it's clear that, you know, in polynomial number of steps you converge, right? Okay, so that's it. So this is the analysis. And the key thing I want to tell you about, you look at this analysis, it's extremely simple. We'll have to do exactly the same when we are trying to solve the non-commutative singularity. Okay, questions?
It's kind of, is there any understanding of which of the many solutions it picks?
Yeah. Actually, it doesn't pick a solution. That's a good question. What happens is that it will do the following, this algorithm. It will shrink to 0 all edges that don't participate in any perfect matching. And we leave with positive values those that do.
Oh, I see. The union of all those.
Yeah. Every edge. Yeah. Now the values, the distribution of values is a different question. But anyway.
The non-zeros are there.
Yeah. The non-zeros will be edges that participate in some perfect matching. The zeros will be. Yeah.
So it's some convex combination of perfect matching.
Yeah. Some convex combination of the perfect matching. Yeah.
Not necessarily even convex.
It will be yeah. So I just want to stress, you know, everybody learned an algorithm for perfect matching in school, in college. I don't know, it's not this one, and I don't know a simpler one, at least to program. It's just 2 lines of code. So, okay, now I want to move to the operator scaling story. Okay, so now we are going to look at the real problem of non-commutative singularity, and I'll explain what operator scaling is in a second. And yes?
Can you also recover a perfect matching from the output of the scaling algorithm?
There is an obvious way to do it. You start removing edges, but self-reducibility. I don't know a direct one, like a parallel one. Yeah. Okay. So I want to tell you about a quantum leap. So about a paper of Gurwitz, which the pun is intended. It's a quantum leap, but it's also a quantum information theory approach, okay? So, and this is the beginning of this connection of this problem to different areas, and we'll see others. So here's the problem we looked at, the algebraic problem. We get a tuple of matrices, we generate this symbolic matrix from it, and we ask whether it's singular. It's a singular matrix. The PIT question was whether it's commutatively singular, or we asked whether it's non-commutatively singular. And that's a problem Gurwitz wanted to solve. And he said, well, we can look at the tuple of matrices differently, and here's a useful way to look at it. You can look at it as what is called a completely positive map, or completely positive operator. So again, a tuple of matrices can be viewed as an operator on matrices, and this is what you do to a matrix. What it does to a matrix is simply sums up AI transpose, or dagger, if it's complex. Okay, so it's a linear map on matrices. This is a quantum generalization. A positive matrix is a linear map on vectors. This is a linear map on, now a tuple of matrices is a linear map on matrices. And it takes positive matrices to positive matrices. In fact, that's why they are interested in this in quantum information theory. This is a, you know, you usually have P be a density matrix, namely a quantum state. And this is an operation, that's the most general operation you can physically implement on quantum state.
So AIs have no constraints?
No constraints, but any complex matrices, yes. That's called a completely positive, there's no constraint. I mean, if you really want to implement it, you need to implement these matrices, yes. But yeah, there's no constraint. What?
They don't have to be 100%?
No. This takes care of everything. You don't, yeah. And he said, okay, we have an operator, let's ask a question. In fact, the question he asked should remind you of the whole condition in perfect matching. Does some set shrink? Here, It's not whether a set shrinks, it's an algebraic version, is whether some matrix, the rank shrinks. So is there an input that you feed to this operator so that you get at the output a matrix of rank smaller than what you started with? This should be the analog of no perfect matching, right? That's what he was asking. And in fact, he showed that, if this is the case, then, right, it's the same tuple here, so you can translate. This implies that the matrix is singular. That's very easy to see. The tuple is invertible, is not invertible, is singular in the commutative case. But it was not if and only if, and that was the problem. Never mind that it's a problem, we'll see what else he did, which is, it's really amazing and useful. And the next thing he did, he wanted to use the algorithm we saw before. And for this, we need a notion of double stochasticity, right? So we saw that, positive map is some analog, some quantum analog of positive matrix. What's the analog of being doubly stochastic? Here's the analog. Basically, the analog is that when you apply to the identity, you get the identity back. And when you apply the dual operator, just reversing the order of dagger, you get the identity. So this is, I want to, convince you that this is like in the matrix case. A matrix is doubly stochastic. When you apply it to the all ones vector, you get the all ones vector. And also when you apply the transport. It's the same thing. So there is a notion of double stochasticity. And the thing that started, or one of the connections that started our work, the recent work, is that, we were asking this question, is an old result of Kohn that says that in this case, if you are talking about non-commutative singularity, then in fact it's equivalent to this rank shrinking condition. So that was, that's why, if we solve this problem, we solve this problem. Now, at a high level, so it was just a definition at this point, no algorithm yet. I just want to say that from a high-level point of view, towards the algorithm, this is the analogy between the two problems, matrix scaling and operator scaling. So we'll simply try to scale an operator like we scale the matrix. In the matrix scaling, the input was a positive matrix. Let me put them up. We want to make it doubly stochastic by applying from the left and the right diagonal matrices. And with a positive operator, we have a tuple of matrices, and we'll try to make them doubly stochastic, again, by multiplying them on the left and the right by any invertible matrices, not necessarily diagonal. That's a natural quantum generalization. Okay? Okay, so let's do it. How do we do it? I'll just write down, I'll copy what we had before. So these are just the same condition. The input is a tuple of matrices. We want to scale them, as I said, to what it means to be doubly stochastic. Scaling factors, like before, if it's not stochastic, you multiply it by something to make it stochastic. It's the same thing as before. So here it is. There are scaling factors that are obvious from the input, from the data. You run the same algorithm, simultaneously satisfying both rows and columns. Analog of rows and columns is hard, so you do rows, you do columns, you do rows, you do columns. So you multiply from the left, from the right, this is the algorithm. It's the same algorithm. And you test whether you are close to this sense of double stochasticity. And it turns out that if the answer is yes, then it's non-singular, and if the answer is no, it's singular in the non-commutative setting. So this just says it solves the problem. It doesn't explain why. But at least, as I meant it to look, it looks exactly like the algorithm for matrix scaling, and it is. So how do you analyze this one? You analyze it the same way. You first need a progress measure. And now, the next ingenious thing that Gurwitz did was pick a progress measure. He tried actually in the paper doing a quantum permanent, which you can define, but turns out to be no good. So permanent didn't work. And he suggested to use what he called the capacity. Now this notion capacity was shown in a paper with Peter Yanilos a few years before, with Gurwitz and Yanilos, to work in the case of matrix scaling. And what Gurwitz did here is generalize it. So what is this capacity? It's a really interesting function. First of all, it's interesting because it's not a convex function, and because we will be able to compute it efficiently. So again, you look at the relationship between the output of this operator and the input of the operator, but now you compare their determinants. So you remember these are positive matrices that you feed in. So these are positive numbers. And you look at how small can the ratio be. And in particular, will this ratio go to 0 as you take the infimum here. And then it turns out that using the equivalence I told you before, you can prove that these conditions are equivalent to having positive capacity or 0 capacity. So that's what you want. It's like with permanent being 0 or positive. And the analysis, once you have this, is again the same. It turns out you just like magic. In fact, you don't even have to think. Proving that the capacity is upper bounded by 1 is easy. Proving that it grows by a non-trivial factor, if it can, is easy. It's the same AMG. I mean, in fact, nothing changes. And the thing that didn't work, which was easy in the case of matrices, and here Gurwitz couldn't do it, is proving that if this capacity is 0, then you have a non-trivial lower bound. And this is the main result of this, this paper, proving this. And somehow this is much harder. In the case of matrices, it was really easy, and this is much harder and somehow much deeper. So before I go and explain a little about this, I want to tell you this solves the non-singularity problem in non-commutative singularity in polynomial time, but as I mentioned, it computes capacity, and this is a non-convex optimization problem which can be done by this alternate minimization algorithm.
So is there some connection to like Grassmannians or Stiefel manifold or something, like with that?
Grassmannian of?
That thing, yeah. So the first line, the AI transpose.
Yeah.
That's the Stiefel manifold, right? AI transpose equals I.
For one matrix?
For one.
Yeah. My one matrix
so
is just no. It's much. No.
No connection.
It's it's not that it's much more general. It's a much more general.
Yeah, sure.
For one matrix is unitary. If you have, for one matrix, it just says that the matrix is unitary.
Right.
AI, so it's a much. It's a yeah.
So is the capacity used for anything else?
That's a very good question, and we'll see it's coming. So it's not, he made it up because it's a natural quantum generalization of the classical capacity. It has, as far as I know, no quantum information theoretic meaning. Okay, so I don't know. But it will come up, well, at least. It comes up in other places. I don't know of an intuition.
Something that is meaningless.
It's exactly, but it's not convex.
Was this Gurwitz's goal all the way back in 2004?
Yeah, that was the goal to solve the commutative singularity.
Oh, commutative.
The Edmonds problem.
I see.
And it didn't work, and it didn't work because it couldn't work because it's not equivalent. Yeah. But even that, we're also proving so there are two issues. One is the connection, it has to be to non-commutative, and the other is proving some lower bounds to start, yeah.
So is this for the matrix scaling an algorithm not based on this alternating minimization, but something convex like semi-definite programming?
Yes.
Relaxation?
Yeah, definitely, that's a good point. For the matrix scaling case, the way I presented the problem of matrix scaling is not a convex formulation. However, if you move to exponential variables, so you write the variables in xi as e to the yi, then it becomes an instance of geometric programming, and you can, However, this cannot be done here. Something else could be done here. Maybe I'll talk about it later.
Cannot be done what? Where?
Change of variables that will make this capacity convex. Okay, this can be done in the matrix scaling case. Okay. So I want to tell you, first of all, in order to compute this low bound on capacity, we have to get into other areas, as I mentioned. And this is, so as you, As we are working on it, we were sort of amazed by the richness of places in mathematics where you see matrix tuples and they have different meanings and all meaningful meanings and actually connect with each other really nicely. So we saw it as a symbolic matrix. We saw it as a positive operator. In non-commutative algebra, it turns out to capture rational expressions, formulas. In invariant theory, it turns out to capture orbits in certain group action. I'll talk about this, I think. In analysis, it turns out to be a template for a famous set of inequalities called Braskamp-Lib inequalities. And in optimization, it turns out to be a way to describe exponential size linear programs that we can solve, we can test membership for. So, so all these problems turns out because of these connections to be in polynomial time. This we saw, this I'll show you, I'll talk a little about that, these connections, and this I guess I won't. Okay. So I want to talk a little bit about the connections to these two fields, and I want to tell you what they are. Now it will be sort of ridiculous that I'll tell you about these fields that mathematicians worked on for over 100 years in one slide each, but I will, and it will be sort of impressionistic. I want to tell you where are these connections feeding into the analysis of the algorithm, okay? And first I'll show you this slide. What exactly comes up in those places. So this is what comes up. So it turns out that for the analysis of the algorithm, in fact for proving this lower bound, doesn't matter how, you need to take the tensor product of two operators, which is a very natural thing in quantum information theory. So you can have two tuples, each representing an operator. You can take the measure you want to understand is this thing, the determinant of the sum of these tensor products. These are the new matrices in the new operator. So this is the kind of thing you would like to understand. And it so happens that in all these three fields, these expressions come up extremely naturally for completely different reasons, exactly the same expression. So rather than going over this, I'll tell you in more detail. Here, I'm just in the analysis, it comes in through some inequality, how this capacity of the tensor product relates to the capacities of the original constituents. That's the key to the lower bound. But I want to show you a little bit about these two, okay? Where this expression comes up. So, non-commutative algebra, okay, so the order in which you do things matters in life, and even in most of mathematics, not all, but in most. So, just maybe questions before I go to these two subjects? Okay. So I want to explain, finally explain the problem we are solving, this non-commutative singularity. What is this problem? It's actually an extremely natural problem. So what is non-commutative algebra and what's this word problem? So, okay, non-commutative algebra, you simply have a bunch of non-commuting variables, multiplicatively non-commuting over some field, normal field, like the real, the rational, the F3. And at least what polynomials is, the ring of polynomials is still something that is very simple to understand. It's exactly like the ring of polynomials in the commutative case, only you have more monomials. X, Y, and YX are not the same. That's all. So this you can understand. And you want to do the same thing you do in the commutative case. You want to have division. In order to have division, you need more functions. What do they look like? And you want to create a field. So all the rational expressions. And unlike the commutative case where every rational function is a ratio of two polynomials, here it's not. And here the only definition that you can make, or was made to begin with, is just start from the variables and from constants in the field and add them, multiply them, invert them. This just generates expressions. Now here's a very simple expression, just to illustrate the complexity of this. X inverse plus Y inverse. Even this cannot be written as a ratio of polynomials. You can check, it's a really nice exercise when they don't commute. Okay? So it's weird, and it's getting weirder. Here's, a really very, very powerful and important result of Rethenauer. Look at this expression. This expression has nested inversion. You invert y here, and then you invert on the outside. Right? Well, in commutative case, you can eliminate. There are no nested inversions, right? Well, he proved that this one cannot be eliminated. And in fact, you can write expressions down where there's an arbitrary nesting of inversions which cannot be shrunk by even one. And then let's raise the question, what happens? Here's another very similar expression, but just with two variables. Nested inversion here, it can be eliminated. This is a famous identity, the Hua identity, is the fundamental theorem of projective geometry, for those who know. So people are interested in identities in the non-commutative case as well, very interested, and the question of proving them is interesting there.
We do at least have here the left inverse and the right inverse of the same.
Yeah, it's not the same. Left inverse and right. Of a single thing, it are the same, yeah. Anyway, so you would like to know whether the left is equal to the right or not. So this is that's a word problem, or that's a PIT problem in the non-commutative case. So so what does it have to do with our problem? I should probably say that this result, if you don't have divisions, if you just have polynomials, then to Mark's question before, a randomized algorithm was known by plugging matrices to the variables, small matrices to the variables. But actually, Ranraz and Amir Shpilka found a deterministic polynomial identity testing if there is no division, so they are just polynomials. But in this case, so as I said, it was not even clear that decidability is there. And I want to show you, so we'll show it in P, and I want to show you where these expressions come in. And again, like Mark says, it's very natural when you have an expression in non-commutative variables to just plug in matrices for the variables, or like Noah said before, right? So Amitzur proved a very strong theorem. So a rational identity is zero. What you would think is, if I plug, just plug everything you can to the variables, if it's always zero or undefined, then you are fine. And what Amitzur added is a determinant. So instead of looking at whether a huge matrix is full of zeros, might as well test the determinant, a single number. So somehow it's either, if an expression is non-zero, you already get a non-singular matrix out sometime. And that's exactly where our determinant will come from, and that's the subject of the second theorem, where are the matrices. So here are the matrices. What Kohn did in another construction of this free skew field, he proved that any rational expression can be turned into a sequence of matrices such that this expression is zero exactly if this symbolic matrix is singular. Okay? So you can take any formula with division and translate it to a symbolic matrix, and one is zero if the other is singular. What does this remind you of from the beginning of the talk? Which theorem?
The Valiant.
Valiant theorem. So notice, the Valiant proved exactly the same for the commutative case. The completeness of the determinant for
So Kohn doesn't imply anything for commutative?
It does.
So he proved Valiant theorem?
He proved Valiant theorem before Valiant. Of course, it was like in a galaxy far, far away, right? It's
highly coded.
In a non-commutative. Also, yes. Yes.
So in terms of intuition for singular, so how much of the commutative intuition survives? So you define singularity in terms of this specific expression for the determinant?
But it's not determinant. You have to ask about whether it's inverted. There is no determinant, no meaningful way to define determinant in the non-commutative case. So instead, you plug in, so let me finish this, right? You plug in now matrices for your variables, right? And then it becomes commutative. But they have to be bigger matrices and not...
But it's not like there is a symbolic element in the kernel of something.
No. There is no linear algebra there. There is no linear algebra in the sense that you can... or at least
For high enough D, eventually there
we will talk about this in a second. But notice that this says that you have to plug, at least the theorem says, that you have to plug matrices to your variables, but it doesn't tell you which size matrices. You have to try them all of all sizes. This is what the theorem says. Okay, in fact,
there exists A1 through AN with unspecified degree?
No. These are matrices. In this existence, you are talking about this.
Yeah, so
this is the direction. Yeah, I'll tell you, but I just want to answer, maybe clarify one thing before. This transformation, like invariant, is completely explicit. Fine. You get the formula, you create the matrices. Yeah. Okay. Here, right, you have a singularity of a symbolic matrix, and it's, it's singular if and only if this determinant is 0, is always 0, no matter what you plug to the variables. And no matter what you plug has to be matrices of arbitrary sizes. All possible matrices of the field of all sizes. That's at least a theorem in non-commutative.
Singularity of an expression.
Like this.
That's the definition. That's the definition.
You can define it by defining the free skew field, but it turns out to be equivalent to this. That's in fact what Kohn was set out to do, to have a new definition. Amitsur had defined the free skew field. It's not clear that it exists, I should have said. It's not clear that there is a completion of polynomials that includes division in non-commutative algebra. There are rings for which you cannot do it. But somehow, magically, for the ring of polynomials, it can be done. So this is one place where this expression appears. And that's one key to the puzzle. And now I want to tell you where the other key is. Okay, so everybody's happy with this? This was my one slide on invariant theory, on non-commutative algebra. It's a really bizarre object, this field. Okay. And we will come back to the questions Mark has been asking from the beginning, bound, give bound. I mean, so for all D, what do we do? Okay, so where do we get bounds on B? This is exactly where invariant theory is going to help us. Okay. So what's invariant theory in pictures? You want to understand group actions with just symmetries of objects, and you want to understand the way the group acts on some objects. What are the trajectories of this action? So here are some pictures. This you know, right? Graph isomorphism, symmetric groups act on the vertices of a graph, right? And this is two guys in the same orbit. It's really the same graph reshuffled. Here's another one. Here the group is just time. You hit the white ball and then you look what happens, right? Maybe this is in the orbit of this. If you knew the momentum and...
Wait, what is this group? I mean,
the group is a real line. You start, is a real numbers. I mean, just time. The group is time. It evolves with time. You start it, and it evolves with time.
What's the group here? With the balls, I mean, I don't understand.
Yeah, time. You see after another second, here is maybe you apply a permutation, that's a group, yeah. It's simple, it's too simple. Here's another group. What's the group here? Well, it's a group of, you are allowed to, right? It's really a group. You are allowed to cut the shapes, right, and move them about. It's really a group.
Uncut too.
Excuse me?
You have to be able to uncut too.
Sorry?
You have to be able to uncut.
You don't uncut. You can move them about so they look like yeah. You just cut and move them about. Yeah. And then one of the basic questions that we care about for this analysis, so I guess I will just stop probably after the invariant theory unless you want to hear more, but the one basic question in invariant theory is what are the invariants of such actions? What doesn't change when you change this? So you can probably tell me what doesn't change when you do this. Area doesn't change. And another important question in invariant theory, are these the only invariants? So okay, you found an invariant. Is there another invariant? I mean, are two things of same area can be moved from one to the other using this simple operation? What do you think? No? Yes? Any yes? Yes. So the answer is yes, and it's easy to prove. It's a nice exercise. It's so. Now here's another question. Suppose we do it in 3 space.
That's not true.
I give you... Can I ask a question? Now these are wooden blocks.
Answer question.
Yeah. I give you, instead of this, I give you wooden blocks, polygonal thing, and I give you a chainsaw or something. And you can cut and I ask you what's an invariant. You'll say, well, of course, the volume is an invariant, sure. But is it the only invariant? That is a tough question. This is Hilbert's first question in the famous list of questions. But it was the first one to be solved. And his student Max then found another invariant. Anyway, this was...
Invariant by Banach-Tarski.
Sorry?
You have to be careful about how you define it.
Yeah. I'm not going there. The chainsaw has no... Yeah. That's a very good point. Anyway, so you look for invariants. That's what invariant theorists do. What are invariants here? Well, you know, this. So here's the area, here's the energy and momentum, right? You remember high school physics. These are all the invariants. It turns out they're understood. What the invariants here? Well, we don't know. I mean, it's really complicated. Despite Babai's algorithm, we have no good understanding. So that's the kind of questions they are asking, and here is the questions that we need to ask. So we are looking at groups, linear groups acting on vector spaces. So you have some group of matrices acting on a vector space just by matrix vector product. And if you have an action on a vector, if you think of this vector as a vector of variables, then you can think that you are also acting on the polynomials in these variables. So you just change the variables, the linear change of variables. Maybe you add 5 times z2 to z1 or something. Okay, so these are the actions. And what type of invariants? Turns out that all invariants of these actions are polynomial invariants. These are polynomials, so this is called the invariant ring. The invariant ring of polynomials, it's all polynomials which do not change, like the invariants before. They simply do not change when you move things about. So P of z remains unchanged after applying any element of the group. Okay, let me give you 2 examples that I'm sure you've seen. Okay, so you'll get familiar with this, and then I'll tell you what is the group we need to look at. Here's one exercise. Suppose that this group is Sn, the symmetric group. So I'm just permuting the variables. What are the invariant polynomials? Symmetric polynomials. That's why they are called the symmetric polynomials. Right, and not only that, notice that they are generated by the elementary symmetric polynomials. So there are infinitely many symmetric polynomials, but as an algebra, they are generated by just n polynomials. You know them, the elementary symmetric polynomials. Good, that's one example. Here's another example. Suppose now the vector space is a vector space of matrices, and I act on it by multiplying it on the left and on the right, basically by basis change on the left and on the right? So by a simple linear group action, by a matrix of determinant 1, basis change on the left, basis change on the right. If I do this change, so that's a group that's acting on matrices, what remains invariant? Yeah, the determinant remains invariant. Is there another invariant? There is no other determinant in that all of them are generated by, it's not trace, it's not, all of them. So this, again, very simple. The invariant ring is all polynomials that are just powers of the determinant in this case, very simple. So these are 2 examples that are the dream of an invariant theorist. That's how they would like to understand their, they have a small, efficiently computable, low-degree invariants. That's what they like. And here's the one we have. The one we have, you should have already guessed from this, is we don't change basis on left and on the right for one matrix. We change it on a tuple of matrices, right? That's what we do. So this is a left-right action. Again, two matrices, R and C, rows and columns, acting on this operator by just changing basis simultaneously on the left and on the right. Okay, this is what we need to understand. This is what we need to understand because that's what our algorithm does. the algorithm, right, keeps evolving by multiplying on the left, on the right. So, so what the algorithm does now in this light is just chasing some orbit. It starts from a tuple, and then it moves about in the orbit of the tuple under this action, right? That's why it's relevant. And now, what is the invariant ring? Well, this is a hard work. Was Dirksen and Weyman, Domokos-Zubkov, and Sherfield and Vanderberg around the same time discovered what the invariant ring of this, what are all the polynomials that do not change here. And magically, and this was discovered independently and unrelated to the previous picture, it's the same thing. Now I told you that maybe in non-commutative algebra they didn't care so much about bounds on these matrices, but I also told you that in the invariant theory game, people care very much about what are small sets of generators, what is the smallest degree. In these two cases we had degree n upper bounds on the degrees of the generator. What about here? So this is, you know, it just says that the invariant ring is generated by all these determinants. And, well, let me skip this, that doesn't matter. I mean, what we are after, okay, not, what we are after, what we are trying to understand is whether this tuple, which is not here, well, just this tuple of matrices, is in the, what's called the null cone direction. Basically, is it zero on all invariant polynomials? This basically was the question we were asking, whether all these determinants are zero. That was saying that our matrix tuple was singular. And as we said, this is, well, one can prove that that's equivalent to having capacity zero. But my point is that they studied bounds on D. And the first person who studied this is Hilbert, and he proved that you can put a finite bound here. There's a finite bound, even though it's not clear what it is. It's some function of n. And for those who know which paper I'm talking about is the 1890 paper. This is the same paper in which it's the, you know, he proves the Null-Salazar theorem. That's the same paper where he proves the finite basis theorem. All these theorems and the theory developed are to prove this. He was very interested in this. His motivation was invariant theory. Anyway, there was no bound here. This was doubly exponential. This was exponential. And this was turned out to be enough for what we did. Shortly after we did it, we got, you know, Dirksen and Markham even improved it to a polynomial bound. So back to Mark's question, there is an upper bound which is polynomial on this sides of the matrices. In fact, n for this problem. And so you can plug n by n matrices, and this gives you immediately a trivial. Yeah, random, exactly. There is a bound. It's still for all matrices, right? So, but random would work, yeah. So if you only wanted a randomized algorithm, it will follow from this. Okay, so let me, now I have a lot more, but I need to finish. So what shall I, yeah, so I'll just mention that the alternate, I just want to say, about, so let me take just a couple of minutes to talk about alternate minimization, because it's a message of, you know, this is analyzing some type of alternate minimization algorithm. Alternate minimization algorithms are those where we have a really complex global problem, but all we can do is optimize or solve in some sense when we fix all variables but one, and then we can iterate and alternate between them. And I want to tell you examples we understand well and examples we don't understand well, but I will not do this. So this means that I need to go somewhere to the end. And summarize. So what did we see? So yeah, I want to point out again these really beautiful connections to many areas of math. We saw alternate minimization and scaling algorithms and some analysis for them. We saw that symbolic matrices really appear in lots of places in various forms, and this combination of forms is useful. And the point I made in the beginning is that the problem we started solving was an algebraic problem, and nevertheless the algorithm for it was an analytic algorithm, so a continuous algorithm, this alternate minimization. And furthermore, the analysis of this continuous algorithm used back algebra. Anyway.
It's a continuous algorithm?
It is a continuous. In fact, the continuity is important. It's continuous in the input.
In what?
In the input. It's continuous in the input. The scaling factors just computed as, you know.
But you're still, I mean, you're computing all purely algebraic things. It's not like you're doing some calculus or something.
No, but it's not symbolic. No, I don't agree. It's not a symbolic thing. You get these numbers and you start, you know, you need to take inverses of matrices, and yeah, I don't know what, you have to do it numerically. You cannot do it symbolically.
The final test is in particular.
No, but the whole thing is completely, it's a numeric algorithm.
Sums and inverses, I don't.
Exactly. No, but you work with number. You can work symbolically. Okay, so just without returning the slide. One way to test whether this tuple is singular is simply evaluate it on all invariant polynomials. That would be a symbolic algorithm. You just plug them in. And it's identically zero or not identically zero. There's nothing continuous about it or approximation. Yeah, of course, this is an inefficient algorithm.
So you're not using evaluations, you're not using it as a...
No, yeah. I don't know a black box algorithm. Anyway, back to the big open problem is just, solve the commutative problem. I think I'm done. Thank you. No questions?